we are given the following function. F of x is equal to, what have we got here? 8x plus 9x squared. And here are the questions. So the first question is, divide the interval in, over the interval from 0 to 1. And the first part of this is to divide the intervals, n subintervals equal length. How long is each subinterval? Well, the subinterval length is given by the total length. So generally we write that as b minus a divided by n, which in this case is 1 minus 0 divided by n, which is 1. We often call that delta x. And then the second question is, in order to determine an overestimate for the area under the graph of the function, at what x value should you evaluate f of x to determine the height of the first rectangle? Okay, so I'm going to draw a little bit here. And I'm going to note that 8x plus 9x squared, I can factor out an x. So 8 plus 9x. That's an upward opening parabola. And it's got intercepts at 0 and negative, what, 8/9, I think. Specifically 0 and a negative number. So when I draw this parabola, from 0 to 1, the function is definitely increasing. So if I'm looking at my, so let's actually blow this up a little bit. So if I'm looking at, say, let's say 1 is way over here, and here's my first interval, my second interval, my third interval, all the way to my middle. And again, not that you've been doing this in your class, but I typically, I kind of learned the way you're supposed to do this is you call this first point x1, sorry, x0, this is x1, this is x2, this is x3, all the way up to this, the last one is x sub n, and the second to last one is x sub n minus 1. So in this first subinterval, I can either use the left endpoint or the right endpoint or some point in the middle to find the height of my rectangle. But if I want an overestimate, I have to use the point in this first subinterval that's going to have the highest function value, which is going to be the right endpoint since my function is increasing. So I'm going to use that endpoint to find the area of my first rectangle. So the first rectangle, the area is going to be given by the base times the height. The base is the length of the subinterval, which is 1 over n. The height is what you get when you plug in that value to your function. Now, that value is also 1 over n, because we started at 0, and we added 1 subinterval length worth to get to the next one, which is 1 over n. So that's the area of the first rectangle. Now, this question specifically asks, what x value should you evaluate the function? Well, the x value we're evaluating the function at is, in fact, 1 over n. I'm going to tab here. 1 second, sorry. Go ahead. You may leave. All right, so let's see, 1 second here. I'll make it a little smaller here. All right, so that's the answer to the second part of that question. That's the value that you're going to plug in your first rectangle to get the area of the overestimating rectangle. So now the next question is, find a formula for the x value in the kth subinterval, which determines the height of the kth rectangle. So here's the way I'm thinking about it. The first rectangle, we're using x sub 1, which is 1 over n. The second rectangle, we're using 2 over n, right? Because at each right endpoint, or whatever, but each next endpoint is one subinterval length, which is delta x, which is 1 over n away from the previous one. So if I really stretch this out, right, if I say like there's 0, there's 1, and I write a bunch of these, there's x1, there's x2, there's x sub k minus 1, there's x sub k, there's x sub n minus 2, there's x sub n minus 1, there's x sub n. So there's all my endpoints. Oh, 0 is x sub 0, or whatever your starting value is, that's your x sub 0. So look, each of these is 1 over n away from the next one. So this first one, x sub 1, is at 1 over n. This next one, x sub 2, is at 2 over n. The next one, x sub 3, would be 1 over n plus 1 over n plus 1 over n, which is 3 over n. And we can see that we just keep adding 1 over n to get to the next endpoint. So I want to get to the kth endpoint. It's going to be 1 over n added 1, 2, 3 k times. Right, this distance, that's k times 1 over n, which makes sense because literally you're saying, well, what's the length of k subintervals? Well, each of them has a width of 1 over n. There are k of them. K times 1 over n is k over n. So that'd be the answer to the next point. So far, none of these are really dependent on what our function was. Well, it depended on the fact that the function was increasing, so that we were using the right endpoint. But it does depend on the interval. So if your interval is like 0 to 2, then each subinterval will be a length of 2 over n. And the point you would plug in to get the height of the function would be k times 2 over n, or 2k over n. Okay, so now we want to write down the Riemann sum for f of x over the given interval using the x. But that's not a very well phrased sentence. So I guess so again, remember the Riemann sum is the sum that is approximating the total area under the curve. So I want to approximate not just the first rectangle, but right the total area under the curve. So I'm doing this, all the way to the last one. So I want to write down a formula using sigma notation for the area under that curve, or the approximate area under that curve. So yeah, I'm going to kind of add in, right, the kth rectangle in the middle here. So here's really the idea that we're going to use. We want to find an expression for the kth rectangle. We know that the first rectangle, sorry, I should say for the area of the kth rectangle. The first rectangle has an area of 1 over n times the height, which is f of 1 over n. The kth rectangle has the same base. So the kth rectangle, the area is the same base, which is the width of our subinterval, which is 1 over n, times the height, which again, we know that we are plugging in x sub k, which is just k times 1 over n. So it's going to be f of k over n. That's the height of our kth rectangle. I mean, sorry, and this expression is the area of our kth rectangle. So now the thing is, we can use that area of the kth rectangle and say, well, look, if I set k equal to 1, I get the area of the first rectangle. If k is 1, I get 1 over n times f of 1 over n. If k is 2, I get the area of the second rectangle. 1 over n times f of 2 over n, which is going to be this rectangle right there, and so on. So the idea is that you can let k index from 1 to n to get all of the rectangle areas, so that the total area is approximately, right, because it's an approximation, the sum from k equals 1 to n of 1 over n times f of k over n. And then we should actually use the function that we're given. So my function is 8x plus 9x squared. So this is going to look like the sum from k equals 1 to n of, I'm going to put the 1 over n at the end. F of x is 8x plus 9 squared. F of k over n is 8 times k over n plus 9 times k over n squared. That's how you would answer the next part, I guess the fourth part of that question. And then they say, so, okay. So the next part, I feel like the question is a little confusing. It's not phrased really the way I would write it. But the next part says, using the formulas for the sum of k and the sum of k squared, write down the above Riemann sum, so this same Riemann sum, without using a sigma. The idea here is basically that you want to re-express this, break it apart, or multiply it out, break it apart, and then use the formulas. So that's what we're going to do. So I've got, again, the sum from k equals 1 to n. By the way, do stop me if you have questions. What did I say? 8. Yeah. 8 times k over n plus 9 times k over n squared times 1. Looks good. So then we're going to distribute a bit. So I'm going to distribute the 1 over n in. So I'm going to get the sum from k equals 1 to n. 1 over n times 8k over n is going to be 8k over n squared. And 1 over n times 9 times k over n squared is going to be 9k squared over n cubed. And we're feeling good about this because our powers of k are 1 less than our powers of n. Great. So then we're going to break. So this would come, no, this is the not be, right? We want to write without a summation. So you keep going. So we're going to break this apart into 2 summations. The sum of 8k over n squared plus the sum of 9k squared over n cubed from k equals 1 to n, k equals 1 to n. And then we're going to pull out all the non-k constants, right? Because k, well, actually all the non-k terms, right? Because k is a variable, it's changing, right? It's 1, then 2, then 3, then 4, then 5. Whereas 8 and n are not variables as far as the sum is concerned. So then we're going to write this as 8 over n squared times the sum from k equals 1 to n of k plus this, 9 over n cubed times the sum from k equals 1 to n of k squared. And now we can use the given formulas. We can say that this is equal to 8 over n squared times the sum from k equals 1 to n of k, which is n times n plus 1 over 2, plus 9 over n cubed times the sum from k equals 1 to n of k squared, which is n times n plus 1 times 2n plus 1 all over 6. And if I was trying to type this into web work, I would probably try and simplify it just a tiny bit so there's less typing to do. I can cancel an n here and an n here. I can cancel a 2 here and a 2 here. So this first part here is 4 times n plus 1 all over n. Here, I can cancel an n here and an n here. I can cancel a 3 there and a 3 there. So I'm left with 3 times n plus 1 times 2n plus 1 over 2n squared. That's a little nicer looking. So that would be your answer to the second to last part of this question. Here is a way of writing the Riemann sum that no longer uses a summation symbol. Okay, the last part is take the limit of this. Well, that's the easy part. Right, the limit as n goes to infinity of this expression so let me ask everybody, and I am actually asking, for this first part here, what's the limit of that first part? You can type it in the chat. You can type it in the chat. Excellent. Okay, this next one's slightly harder. What's the limit of this part? right? It's 3. So it is 3, not 3/2. And here's why. If you multiply out the top, you don't get 3n squared, you get 6n squared. So this part here, right, that looks like 6n squared plus some smaller terms divided by 2n squared. And the limit of that's going to be 6/2, which is 3. So be careful with the, So be careful with the k-squared formula. There's always that extra 2 lurking in there. It's going to double your value from what you might think it would be to what it actually is. So yeah, so our answer is 7.
Professor, James, I have a quick question. So on that part, can you explain that process again of like getting the limit of 3?
Sure. So here's what we're really, so I'm gonna, I'll resume this thing here. So let me say first one thing. Do you know what this limit is? Anybody? The limit is x goes to infinity of 73 x to the 4th plus 2x cubed plus 90 x minus 1 over 5x to the 4th plus 7x squared minus 6. Can anybody tell me what this limit is? The answer should be yes. Everyone should be able to tell me exactly. It's 73/5. The reason it's 73/5 is because yes, we'll get there. So the reason it's 73/5, you can either, so there's like 3 ways you can do this. You can use the rule. It says if you've got a limit to infinity of a rational function, where the degree on top and the degree on the bottom are the same, then that limit is equal to the fraction or quotient of the leading coefficients, meaning the coefficients of the highest power terms. Or you could use L'Hopital's rule 4 times. I don't want to do that. Or you could actually show the work, which we don't. So we used to show the work, and they're like, we know the rule. But the work would be to divide everything by x to the 4th. So we divide everything by x to the 4th. This is 73 plus 2 over x plus 90 over x cubed minus 1 over x to the 4th over 5 plus 7 over x squared minus 6 over x to the 4th. And then all these things being divided by some power of x, all those go to 0. So you get 73/5. That's exactly what's happening with this. So when I look at the limit as n goes to infinity of 4 times n plus 1 over n plus forgot what it was, 3 times n plus 1 times 2n plus 1 over, what was it, 2, I think? Yeah, 2n squared. Now, this one, what we're really saying is, look, if I actually multiply them out, I don't need to multiply them out, but I'm going to. We don't need to, though, because we can see that if we multiply this out, on top, the leading term would be 4n. On the bottom, the leading term would be n. Since the degrees are the same, the limit is the quotient of leading coefficients, 4 over 1. Same deal here. If you multiply this out, you get 6n squared plus some smaller terms over 2n squared. And again, the quotient of the leading coefficients is going to be 6/2, which is 3. But you multiply it out as well. And this is going to be the limit as n goes to infinity of 4n plus 1 over n, plus this is going to multiply out as 6n squared, 2n plus n is 3n plus 9n plus 3 all over 2n squared. So you can either use the rule, or literally, since each one has a denominator, just one term, you could actually do the division. Again, I don't think you need to. I think it's perfectly reasonable for you to go straight from here to saying it's 4 plus 3. But you can say, oh, look, that's the limit as n goes to infinity of each thing is divided by n. So 4n divided by n is 4 plus 1 over n. And then 6n squared over 2n squared is 3. 9n over 2n squared is 9 over 2n. And 3 over 2n squared is 3 over 2n squared. And look, these parts go to 0. So you get 4 plus 3, which is 7. So the nice thing about these particular problems, where you're finding the area under the curve using the limit definition, usually of a polynomial, is that this kind of thing always happens. You do all this work, you rewrite the Riemann sum in this interesting way, and then you're always able to take the limit just using this rule that we have a rational function. The degree on top and the degree on the bottom are the same. So the limit is the fraction of those leading coefficients. Always comes out that way for polynomials. Other questions about this one?
I get that now, but I had like another question on I think which one was it? I think it was the final formula for the x value in the k subinterval, which determines the height of the k rectangle. What threw me off is like how you did like the number line, like the k like x, or I don't know what you did, but I don't know.
Yeah, so I'm going to do two examples like this. So let's look at the one we're doing. So we're going from 0 to 1. And we've got n subintervals. So this is my, and I'm going to draw like some function. So just to kind of label some things. So okay, so this is my first subinterval. This is my second subinterval. Third, fourth, kth, nth. Let's look at, so I've drawn my picture a little misleading, right? Because the actual function we were dealing with was increasing all the time, which meant we were always using the right endpoint because that's going to give you an overestimate. So I'm gonna pretend like I've drawn it that way because I want to redraw it. So we know we're always using the right endpoint, and we know that each of these subintervals has a width of 1 over n. So this is 1 over n. This is 1 over n. This is 1 over n. All of these are 1 over n. Okay. So knowing that I'm using the right endpoint because that's giving me the overestimate if my function is increasing, which it is in this example. And just generally, you always want to use the right endpoints. It's just true. The right endpoints are the easiest. So I started at 0. For this first subinterval, what's the x coordinate of the right endpoint? Anybody? Anybody?
Would it be k1?
So I'm not giving it a name. I'm literally asking what its value is. So I started at 0. I added this much. What do I get?
It would be 1 over n.
Exactly. So that point there, which I like to call x sub 1, but I do not have to call x sub 1, is 1 over n. Okay. What about the right endpoint of the second subinterval? What's that going to be?
2 over n?
Exactly. How about the right endpoint of the third subinterval?
That would be 3 over n.
Exactly. How about the right endpoint of the fourth subinterval?
Then 4 over n.
Okay, how about the right endpoint of the kth subinterval?
It would be k over n?
Exactly. Or if you prefer, k times 1 over n.
So on that part, James, so like k is just like a unknown number pretty much.
Well, I wouldn't necessarily say it's unknown. I would say that it is ranging over all the values from 1 to n. So it's kind of like a placeholder. We're saying, I want to be able to write some arbitrary interval, the kth subinterval, in a way so that then I can write it as a sum. Right? So if I say the area of the kth rectangle, right, which I'm going to write like that. I'm using the right endpoint. Let's pretend it's up like this. The area of that rectangle is the base times the height. And then to add up all the rectangles, it's the first rectangle, so 1 over n times f of 1 over n. The second rectangle, 1 over n times f of 2 over n. The third rectangle, 1 over n times f of 3 over n, plus all the way to the kth rectangle, 1 over n times f of k over n, all the way to the last rectangle, which is 1 over n times f of n over n. Yes, I know that n over n is 1, but I'm going to write it as f of n over n. Now, the reason I'm pointing this out is because then we can use our sigma notation to not have to write all this garbage out. We can say, hey, look, I can factor out 1 over n, and the rest of it is the sum from k equals 1 to n of f of k over n. Except usually we put this 1 over n in, but it doesn't really matter. So letting k equal 1, we get f of 1 over n times 1 over n. Letting k equal 2, we get f of 2 over n times 1 over n. Letting k equal 3, we get f of 3 over n times 1 over n. All the way to the last one, letting k equal n, we get f of n over n times 1 over n.
Oh, so k represents a value in the interval, pretty much.
K represents the numbers 1 through n.
Mm-hmm.
K is what we call an index. It is indexing up, starting at 1, hitting every integer until you get to the last integer, which is n.
Mm-hmm. Okay, yeah. See, I was a little bit confused on that. Now I get it much more. For sure. Yeah, the whole like equation, the whole like concept got me confused. I get it much more.
It is a bit of a challenging concept for sure. Maybe more than a bit, to be perfectly honest. It can be challenging. So somebody else asked about problem 14, which I'm happy to look at. I would point out we definitely did do one like this last time. That doesn't mean I'm not happy to do one again. That's why I'm really recommending this. This is definitely a problem similar to one we did before. So the one I'm seeing in my notes is this integral. The integral, or my homework assignment, is the integral from -6 to 6 of the square root of 36 minus x squared dx. What I'll say about this is later on, we will definitely learn how to do this the hard way, where you actually anti-differentiate this function using the fundamental theorem of calculus, part 2, to evaluate it. But here, the idea is we're supposed to recognize that this particular equation has a shape that we are familiar with via geometry. So if you look at the equation, y equal to the square root of 36 minus x squared, it might catch you off guard at first, but if you square both sides, and then add x squared to the left, you get x squared plus y squared equal to 36. And that is the equation of a circle with center at the origin and radius 6. Now, the thing about this is, I don't get the entire circle. Here in this equation, x can be positive or negative, y can be positive or negative. So you get the point like, for example, 6, 0, and negative 6, 0, and 0, 6. And you would also get the bottom half of the circle, right? Where y is also negative. But this equation, y can't be negative, right? Square roots only give you positive results. So we only get the top half of this circle. So then we want the area under the curve from all the way from -6 to +6. So we want all this area. Well, I don't know how to integrate that, but I certainly know how to find the area of half of the circle. It's 1/2 pi times your radius squared. And that's it. So the idea here, and this almost always shows up on an exam, where people are like, well, they should know how to do this, but it's kind of tricky. But if you know the trick, it's super not hard at all. So be on the lookout for that, right? If you see limits of integration that are opposites of each other like this, and the square root of that number squared minus x squared, it's like, oh yeah, that's a circle or half a circle. Now, the other thing people sometimes tend to ask, which I also would ask, is what's the integral from red? The integral from, say, -6 to 0. That's a 0. of the square root of 36 minus x squared dx. Well, now I'm starting at -6, but I'm ending at 0. So I'm only getting this part of the circle, which is a quarter of a circle. So I'm going to get 1/4 times pi times my radius squared. Here that ends up being, this ends up being 18 pi, this ends up being 9 pi. So just be on the lookout, right? If you see this sort of thing, square root of some square number, doesn't actually have to be a square number, but it's likely to be a square number. The square root of one of your limits of integration squared minus x squared, you got a circle or a half a circle or whatever you want to think about it as. Okay. You guys, are there other homework problems that were troubling anybody? Not that we're here just to do homework, but it's always, I'm always happy to like, why was 6 plugged in? I didn't plug in 6. What I did was I said, this is equal to, right, so it's area under a curve. So this is equal to the area of 1/2 of a circle with radius 6. This is equal to 1/4 of the area of a circle with radius 6. So that's what's happening here, right? I'm not plugging in either of these limits of integration. Yes, that number 6 happens to be the same as the radius, and it is. I mean, it's always gonna be that way. Right here, right? So right here, there wasn't a 6 to plug in. I still used 6 because 6 is still the radius. So right, we're not doing anything with the. We're not using the fundamental theorem of calculus set to do the antiderivative and plugging in limits of integration. We're just using our geometry knowledge. Be like, oh yeah, it's a circle. I know how to find the area of a circle. No big deal. No big deal. Circles are cool. Let's see. Someone asked about. Oh yeah, we can look at this one. So a number of people have asked me about this question in a variety of arenas. A variety of places. So let's take a look at this one. Number 12. This is the setup I have. We have the integral from 0 to 3 of f of x dx is equal to 7. Remember to forget. Let me write myself a note real quick here. Forgot to take attendance in my earlier class today. It's always harder to enter if I don't take the screenshot. So I take the screenshot, your names are mostly in alphabetical order by first name, which is how I have it set up in Canvas. But when I look, if I have to go look at the Zoom report, it is not alphabetical at all, which is a pain in the butt. It's like ordered by who was in class the longest. Anyway, so here's what we've got for problem 12. The integral from 0 to 3 of f of x dx equals to 7. The integral from 0 to 1 of f of x dx equals to 6. And the integral from 2 to 3 of f of x dx equal to 8. And they're asking us about the integral from 1 to 2. That's the first part. Okay, so here, 1 to 2. So here's what you could say if you didn't want to draw. I'm totally going to draw a picture, but you could say, well, look, 0 to 1 plus 1 to 2 plus 2 to 3 should equal the integral from 0 to 3. So this plus this should equal this. It's still worth drawing the picture. One, two, three. So I know that this bit here from 0 to 1 is 6. And this bit here from 1 to 2 is what I'm trying to find. I know that this bit here from 2 to 3 is 8. And I know that the total area is 14. I mean, sorry, 14, holy. Total area is 7. So I know that this, right, this is what I'm trying to find. 6 plus question mark plus 8 should equal the total area under the curve, which is 7. So that means 14 plus our unknown value is 7, which means our unknown value is -7. It's okay that it's negative, it just means my picture isn't very representative of what's going on. It's perfectly fine. People cool with this part? Questions about this part? Okay, so now we've got that. The second part asks us to do the following. It asks us to find the integral from 2 to 1 of 7 f of x minus 6. So there's a couple things they're trying to get you to see here. They're trying to get you to see that, one, you can break up an integral of multiple pieces as multiple integrals. So you can write this as the integral from 2 to 1 of 7 times f of x dx minus the integral from 2 to 1 of 6. You can also pull out the 7. Right? Constant multiples get to come out of the integral. And then we need to use the fact that the integral from 1 to 2 is the negative of the integral from 2 to 1. So I can rewrite this as -7 integral from 1 to 2 of f of x dx. Change the sign here, so plus the integral from 1 to 2 of 6 dx. Great. We know what this is. We know that the integral from 1 to 2 of x dx, we just found that this was equal to -7 from our work that we did before. This, on the other hand, pretending that we don't know any of the rules for integration yet, like we don't know, we can't anti-differentiate this including the endpoints, you can use the fact, well, I know the area under y equals 6 from 1 to 2. That's looking an awful lot like a rectangle. It is a rectangle with a base of 2 minus 1 and a height of 6. So that's equal to 6 times 2 minus 1. So my total area is, so my answer, not my total area, my answer to this particular question is -7 times -7, which is 49, plus 6 times 1. 55. The point of this is that we are able to use these rules for integration, right? That you can break up an integral of a difference into 2 integrals, and that you can take this constant multiple out in front, and you can change the order of limits of integration by changing the sign of the integral. That's what's going on with that question. Let's see here. Yeah, we got that, we got that, we got that.
Hi,
So,
could you
go ahead.
the 49 again?
One more time.
Could you explain how you got the 49?
Sure. So, looking at just this integral, I've got the integral from 2 to 1 of 7 times f of x dx. The 7 comes out. So then I've got 7 times the integral from 2 to 1 of f of x dx. And then I did two things. I changed the order of the integral of limits of integration. So I have the integral from 1 to 2. By doing that, I had to put a negative out here. And then I'm just using the fact that we found on this side of the board that the integral from 1 to 2 of f of x, we found that that was actually equal to -7. I agree that it's a little confusing because you got -7 and -7 twice. It would have been better if they picked a different number. But that integral is equal to -7. So this part here is -7. So I'm really getting -7 times the integral, which is also -7, which is, they should have chosen better. Oh well.
Got it. Okay, thank you so much.
Right. But I imagine the double -7 is like, why is it showing up twice? Because they're totally different. They just happen to be coincidentally the same number.
Oh, James, I have another quick question.
Sure.
So you, for the other part, when you added the 6 times 2 minus 1 part, did you get it from pretty much in your A and B, 2 minus 1?
Yeah, totally.
Okay, so like we always have to do that with the other part. Why didn't we, like, I think I'm just
I'm
confused on
using a special rule that is only true for constants. So if you integrate a constant, I'm just using the fact that that's giving me the area of a rectangle. So if I draw this, right, if I start at A and I end at B, and my function is y equal to c, then the area under the curve from A to B, well, look, that's a rectangle. What's the base of that rectangle?
the base of the rectangle.
Yeah, what's the length of the base?
Would it just be n?
We're not using subintervals. It's exactly what.
Oh, yeah, of course. B minus A. Yeah.
Or like in this one, 2 minus 1.
Yeah.
Okay, that's the base. What's the height of the rectangle? Exactly. So to find the area under a constant, sure, so I will point out, I imagine many of you or some of you have seen some of this before, so you're kind of like, why does he just like do the antiderivative? We could do that, but that is what we're working towards eventually. You could totally, if you wanted to, say, I'm going to integrate this, the antiderivative of a constant is the constant times x, evaluated from A to B. I plug in the top limit first, I get C times B. I plug in the bottom limit second, I get C times A. And that's exactly C times B minus A. That's the way you could do it using the second part of the fundamental theorem of calculus. But we don't actually need that here, because we know how to find the area of a rectangle without using fancy math. We can just be like, hey, the base is B minus A, the height, well, the function is y equal to c, so the height is c, and the area is b minus a times c. So that's what I was doing here. I was saying the area was the base, which is the difference in the values of limits of integration, times the height, which is just 6.
Okay, I get it now. Thank you, James.
Welcome. So let me ask you all. It says before he actually asks the question. I just want to think about a thing for 1 minute. Yeah. So I feel like we're not really doing that. So I'm trying to kind of get to the place where I'm thinking about what we really want to do. So this feels a little bit silly, but I guess we can do that. Sorry, I'm just trying to decide like a thing here. 1 moment. Let me look at their homework assignments. Yeah. Oh, that's interesting. All right, you guys definitely, okay, we should definitely talk about some definite intervals because they're, that's Morris's homework. I was like, I thought that was due today. That's not due today. So I'm gonna look at the Schulten's assignments one more time. Julian tabs open here. Schulten's.
James, if you heard, we have a quiz as well tomorrow. I'm at for Schulten's. It's she wants us to focus. She even told us what it's going to be on. It's like the definite integral using the formal definition. Pretty much just solving a definite integral using the formal definition.
Let's do 2 more of those then, and then we'll move on to kind of move where we're going to be going to next week. So let's use the limit definition of the integral to evaluate this integral. Let's do the integral. Make it a little challenging. Let's go from 1. We'll do this easy one first because actually there's something I want to do. Let's go from 0 to how Let's just look what I want to be here. I actually want to do, yeah. I'm actually gonna make this kind of general. I want to find the interval from 0 to b of x. And I feel like she's always using I feel like all the questions she's given you guys have been using endpoints that end up being right endpoints. Like I haven't seen really many examples of this where you're using left endpoints. So I would argue that you should do it that way. So let's draw a picture. Here's my function, y equals x. I'm going from 0 to b. Well, the next one will be harder, but I want to do this. I'm going to use this one a little later. So we're trying to find the area, and then the curve is 0 to b. Now, I should mention, you could totally use a formula for this, right? It's a triangle. We know that the area is equal to 1/2 the base times the height. The base is definitely b. The height is also b. I know I didn't draw it, so it's the same, but the height and the base are the same because the function is y equal to x. If x is b, this point here is b comma b. So that would be 1/2 b squared. But we could also do this right the long way, meaning I'm going to write this as a bunch of rectangles. Okay, so we want to find an expression for the sum of the area of the rectangles. So I really want to find an expression for the area of the kth rectangle. So there's my kth rectangle right there. I want to find the base and the height of that kth rectangle. So the base is however wide my subinterval is. My subinterval width, also is delta x, is the total length. The total length of the subinterval is b minus 0, divided by the number of subintervals, which has to be n, because we're going to let that go to infinity. So my delta x is b over n. And then the endpoint that we're going to plug in is the right endpoint. So I'm going to say this again. The first subinterval, the right endpoint is k over n. Sorry, b over n. The second subinterval, the right endpoint is 2 times b over n. The third subinterval, the right endpoint is 3 times b over n. The fourth subinterval, the endpoint is 4 times b over n. The kth subinterval, the right endpoint is k times b over n. So the height of your function is going to be given by, sorry, the height of your rectangle, apologies, of your function. The height of your rectangle is going to be your function evaluated at that right endpoint, which I just said was k times b over n. Okay, so now we're going to write the sum of the areas of the rectangles. So the rectangles, like the Riemann sum, is going to be the sum from k equals 1 to n of our base times our height. So f of bk over n times b over. Again, right, that's the height of the rectangle. That's the height of the kth rectangle. That's the base of the kth rectangle. Height and base gives you the area of the rectangle. And then we get the rectangles where k is 1, right? So that's the first rectangle, right? That's right there, that's b over n. You get f of b over n times b over n. And then for the next rectangle, that's b over n plus b over n, which is 2b over n. And the area of that rectangle is f, when k equals 2, is f of b times 2 over n, which is that, times the base, which is b over n. So you just keep doing this to get the areas of all the rectangles out of it. Okay, now we're going to write it. So f of x is x. So this just becomes f of bk over n is just bk over n. So this is the sum from k equals 1 to n of b k over n times b over n. And simplify, I'm going to bring all of my constants out in front. So the only non-constant is k. So the b over n and times b over, so the b squared over n squared comes out in front. And I'm left with the sum from k equals 1 to n of k. We know the formula for this. It's n times n plus 1 over 2. So this is equal to b squared over n squared times n plus 1 over 2. You can simplify that if you wanted to. Sure, why not? It's b squared n squared plus b squared n over 2n squared. And as n goes to infinity, this expression goes to b squared over 2, the quotient of the leading coefficients. So the integral from 0 to b of x is b squared over 2, which again, we already knew because we know the area of a triangle. But you don't have to know the area of a triangle. Okay, let's do another one, and then we'll come back to this, because we're going to start talking about using the fundamental limit of calculus to find the area under a curve using an antiderivative, which eventually is going to do we're doing like lots all the time. So let's think of something else that's not too terrible. Yeah, I'm gonna change it a bit. So let's. I gotta hold my sock. Oh no, these socks are done for. All right. So let's do the same sort of thing. We want to use the limit definition of the integral. I didn't actually write down limit definition right. I wrote down the sum and then I took the limit of it. I could have written the limit of this, limit of this, limit of this. It probably is fine either way. So let's estimate or find the area under the curve from 1 to 5. Let's make it not too, I'll make it a fraction, why not? Sure. 2x squared minus 5x. Sure, let's go all the way. Let's make it gnarly. 2x squared minus 5x plus 1. And then we'll talk about other stuff as well. So, same idea. I really don't want to make this super hard, right? I'm trying to make this easy as possible. So here's the thing. We know we're going to be working on the limit as n goes to infinity of the sum from k equals 1 to n of f of something, which is going to give you the height of your rectangle, times the base, which I like to call delta x. So, what's the base? What's the width of each subinterval here? Well, what's the total length of the interval? Whoops, wrote the wrong thing. So the total length of my interval is 4, 5 minus 1. And then each subinterval, well, how many subintervals are there? Right, there are n subintervals, so the length of each subinterval is 4 over n. So that has a length of 4 over n, that has a length of 4 over n. I'm going to draw this again. I really want to make it super extra here. So if I'm going from 1 to 4, right, this is 1 to 5. Oh my goodness, 1 to 5. Sorry, keep getting 4 stuck in my head. Right. This subinterval has a length of 4 over n. In fact, they all do. This is 4 over n. This is 4 over n. This is 4 over n. It's 4 over n. which means this point here is 1 plus 4 over n. And this point here is 1 plus 4 over n plus another 4 over n. And this point here is 1 plus 4 over n plus 4 over n plus another 4 over n, or 3 times 4 over n. And so if this is the first subinterval, second subinterval, third subinterval, kth subinterval, we see that the kth subinterval, the right endpoint of it, is 1 plus k times 4 over n. Right, the first one is 1 plus 1 times 4 over n. The second one is 1 plus 2 times 4 over n. The third one, the right endpoint, is 1 plus 3 times 4 over n. And the kth one, the right endpoint, is 1 plus k times 4 over n. Or more generally, the kth right endpoint is always given by the formula a plus k times delta x. Right, your lower limit is a, your upper limit is b. K is just k, and delta x in this case is 4 over n. So right, your kth right endpoint is 1 plus k times 4 over n. Always works if you're using right endpoints, which hopefully you are. All right, so our height is going to be f of that. So things are going to get gross here. Not maybe too far, but is the answer 40? I don't believe the answer is 40. I'm pretty sure the answer has a fraction in it, because you're going to get 2x cubed over 3. You're going to get 125. Yeah, pretty sure it's not an integer. No worries. So what I will say about it, so if you have a question like this on your exam, on your test, I would actually maybe, so I would maybe, like, many of you probably know how to do this the fast way. I would encourage you not to do that, because here's what's going to happen if you do that. You're going to see what the right answer is, assuming you've done it right. And then you're going to do all this work, and maybe you're going to make a small mistake. And then you're going to get some answer that where all your work was mostly right, and maybe you made a small error. All that right work, unless I'm way off base, hopefully your teacher is giving you partial credit, like grading. All that work counts for a lot. So don't get too hung up on making your answer actually be the right value. If you can show that you know all these steps, that is what counts for more of the points, or at least should. Again, you should verify that as a teacher that the work shown is valuable. If you're just looking for a right answer, then that seems kind of silly, because you can go plug it into a calculator. Okay, here's the right answer. Okay, so the height is going to be f of 1 plus 4k over n. So here's where things are going to get messy. I have to plug that into this function. Like this function here, that is my f of x. So here's how things are looking. Not pretty. This is going to be the limit, as n goes to infinity, of the sum from k equals 1 to n of f of 1 plus 4k over n. So that's going to be 2 times 1 plus 4k over n squared minus 5 times 1 plus 4k over n plus 1 all times your delta x, which is 4 over n. You need to multiply this out. There's no other way around it. This is equal to the limit as n goes to infinity of the sum from k equals 1 to n. So I'm going to be a little, so make sure you ask questions if you have them. 1 plus 4k over n squared is 1 plus 8k over n plus 16k squared over n squared times 2. That's going to be 2 plus 16k over n plus 32k squared over n squared. And I want to make sure everyone is super duper cool with that. Right, it's multiplied out, right? A plus b squared is a squared plus 2ab plus b squared. This is my a, this is my b. So 1 plus 4k over n squared is 1 squared plus 2 times 1 times 4k over n plus 4k over n quantity squared, which is all this except we then multiply it by 2. Minus, distribute the 5, minus 5, minus 20k over n plus 1, all times 4 over n. Okay, group the like terms together. So I've got a 2 minus 5 plus 1, that's going to be a minus 2. I forgot the limit. Often people do this without the limit all the way through, and then when you get to like the final, like kind of like the homework problem, then we get to like the final way of writing the expression, then they take the limit. I have always been the kind of person that writes the limit the whole way through. I can't really say why. So the limit is n goes to infinity of the sum from k equals 1 to n. So let's see, I've only got 1k squared, so I've got a 32k squared over n squared. I've got a 16k over n minus a 20k over n. That's going to be a minus 4k over n. And I've got a 2 minus 5 plus 1, which is a minus 2. Times 4 over n. These probably have to be a lot of work. The limit then goes to infinity of multiply the 4 over n. So yeah, I kind of want to write this as 3 sums. So I multiply this through 4 over n times 32k squared over n squared is 128k squared over n cubed. Four over n times minus 4k over n is negative 16k over n squared. And 4 over n times negative 2 is minus 8 over n. All right, I'm going to erase this here. I think I can fit this all on one page, one board. So then I'm going to factor out all the not k things. So this is equal to the limit as n goes to infinity of 128 over n cubed times the sum of k squared minus 16 over n squared times the sum from k equals 1 to n of k minus 8 over n times the sum from k equals 1 to n of 1. Right? If you factor out the 8 over n, there's still a 1 left there. Then we use the formulas. So we've got the limit as n goes to infinity of 128 over n cubed times the formula for k squared is n times n plus 1 times 2n plus 1 over 6 minus 16 over n squared times n plus 1 over 2 minus 8 over n times the sum of 1 is just n. 1 plus 1 plus 1 n times. All right, and then we just take the limit. So looking at this expression, I know and hopefully you guys can see this. Okay, I know it looks a little small because I'm trying to make it fit in. On top, I have 128 times n plus 1 times 2n plus 1. I know on top that my leading term would be 2 times 128 times n cubed. So I'm going to get 2 times 128. On bottom, my leading term is 6n cubed, so I get 6. Minus here, if I multiply this out, I have 16n squared over 2n squared in smaller terms. 16 over 2. Here I would just get minus 8. So my answer is 128 thirds minus 8 is minus 16. You could leave that way, or you could write it as 128 thirds minus 48 thirds is going to be 80 thirds. Gross.
So James, I have another quick question. Sorry. I'm just like I'm like a little lost pretty much on the whole overall, like the whole concept, pretty much like how you solve it out, because our professor gave us like an equation, like a specific equation to solve this out. It was it was f bracket a plus k b minus a over n parentheses and then b minus a over n.
to write that down. And sorry, this is Schulten's or Morris?
Schulten's.
Okay, that's fine. So they're telling you the formula is what again?
F of A plus K B minus A over N.
Right. F of A is the plus K in the parentheses or not?
The A is in the parentheses with everything else. The K B minus A over N.
So plus K.
Yeah, it'll be F bracket A plus K B minus A over N bracket.
Right, slow down. So F bracket.
Mm-hmm. A plus K B minus A over N times B minus A over N.
Okay.
And then bracket B minus A over N.
That.
Yeah, oh, I mean parentheses. Parentheses on the things. Yeah, like that, pretty much.
And this is the formula for what?
Like the definite integral, like
Sure.
the definition.
So let me tell you, this is exactly what we just did.
Okay.
This is F of A plus K times delta X. Right there, delta X. Times delta X. That is your height of the K rectangle. This is the width.
Okay.
So going back to the other side for just a second, in this particular example, I know I erased that part over there, but we have that same formula right here. We have F of A plus K times B minus A over N.
Okay.
Right, our A value is 1, our B
Mhm.
value is 5, so we get 1 plus K times 5 minus 1 over N.
Mm-hmm. Oh, okay, okay. Yeah, I think I just confused myself completely, to be honest. But yeah, it's the same formula.
Totally. Yeah. So the idea is then you're going to take that formula and that's what's going to go in your summation from K equals 1 to N.
Mm-hmm.
Yeah. Okay, so the thing I want to kind of connect this to is the fact that we're going to be using the fundamental theorem of calculus to make our lives easier. So here's what the end result's going to be, is that if I want to say find the same integral from 1 to 5 of x squared, what have I got? X squared, sorry, 2x squared minus 5x plus 1. What we're going to learn is that to calculate this, you can find it by finding the antiderivative of this function. So the antiderivative of that function is 2 times x cubed over 3 minus 5 times x squared over 2 plus 1 times x. You can also throw in a plus c, but you don't need it. Evaluated between 1 and 5. That's what the fundamental theorem of calculus says. If you want to find the area under a curve, you can find it by finding the antiderivative of that curve and then plugging in the higher value minus plugging in the lower value. Let's check to see if we get the same answer. So plug in 5, I get 2 times 5 cubed over 3 minus 5 times 5 squared over 2 plus 5 minus, plug in 1, I get 2 times 1 cubed over 3 minus 5 times 1 squared over 2 plus 1. See what we get. 5 cubed is 125. So I get 2 times 125 is 250 over 3. 5 times 5 squared is also 125. 125 over 2 plus 5 minus 2 times 1/3 is 2/3. Minus a minus is going to be plus 5/2. And minus 1 is minus 1. Okay, let's combine the like fractions, meaning the ones that are the same denominator. So 250 minus 2 is going to be 248 thirds. Negative 125 halves plus 5 halves is negative 120 halves. And minus 1 is 4. So let's see, I've got 248 over 3 minus 120 over 2 is 60 plus 4. Let's just make those both fractions over 3. So I have 248 over 3 minus 180 over 3 plus 12 over 3. This is where I always start to worry, like, am I going to get the same answer? I don't know. So 248 minus, let's add the 12 first. This is going to be 260 over 3 minus 180 over 3, which is 80 over 3. Check. So that's the idea that we're going to kind of work up to, is that you can find the area under a curve by finding the antiderivative, or any antiderivative. We usually use the one that doesn't have another constant. Yeah, right. That's exactly right. I don't imagine on your quiz tomorrow you would be allowed to do this, because she's going to ask you to use the limit definition of the integral, not the fundamental theorem of calculus. But that's where we're going. So, yeah. So sometimes the book does some weird stuff where, I don't know, I don't feel like this is particularly valuable. So I'm just looking at some notes that I have here. Yeah, I don't think. Let me just talk about a couple other. So I suppose I should ask you guys. Yeah, I think it's always kind of like, what do we want to start talking about? I feel like you guys are going to have 2 class periods before I see you again. I feel like I should start preparing for the fundamental theorem of calculus. So let's go ahead and do that. This next part will not be on your quiz tomorrow at all, but I think this is where we need to go. So let's talk about this. And this is a fundamental theorem of calculus, which we often abbreviate as the FTC, part 1. Okay. The breakdown is this. All the fundamental theorem of calculus part 1 really says is that if you take the derivative of the antiderivative, you get the function back to start with. That's it. We're going to write it out in a very kind of complicated way, but that is the real gist. The derivative of the antiderivative is equal to the function that you start with. Great. All right, let's see. The derivative of the antiderivative of a function is equal to that same function. So let's say we've got this. We've got y. I'm going to call y the integral from a to x of f of t. And that's going to be the area under the function f of t between a and x, from t equals a to t equals x. Do I have enough room to draw the picture? I might need to draw the picture on the other side of the board here. But let me do that. I wish I had another board. I don't have the room for another board, but I wish I had another board. So here's the idea. We've got some function. And let's say, I don't know, let's say a is maybe right here. There's a. Sorry, there's a. And this is the t-axis. And somewhere, I don't know, somewhere over here is our x value. So, and hopefully you guys can see that, right, x changes. X is a variable. As x gets bigger, the area under the curve gets bigger. As x gets, right, because this curve is positive, right? Curve negative. Okay, whatever. So let's also make the following assumptions. Suppose that f of t is a function that represents the velocity of a runner, sure, a runner, at time t. So just looking at my picture here the runner was running pretty fast, and then they slowed down a little bit. Here they're running the slowest, and then they start speeding up again. They're still covering distance the whole way, right? Right. No matter what, if they're running slower, they're still capturing some distance or traversing some distance. So if f of t is the velocity of run at time t, then the area under the curve, what do we got here? I'm going to change that. The area under the function f of t represents the distance traveled. Which again, right, makes sense if you think about what the units are. If this is our function f of t, which is measuring velocity, which I'm going to say is in meters per second. This axis is in meters per second, and this time is measured in seconds. Right, if we were going to break this up into rectangles, I'm not going to do that. Right? If we look at, like, say, if we look at this first rectangle here, right? The area would be some, like, maybe 1 second's worth of time times however fast the person's running. Let's say they're running at 6 meters per second. So 1 second times 6 meters per second gets you an area or a distance of 6 meters. So the area under the curve, right, that area, that rectangle, represents the distance traveled. So the total area under the curve represents the total distance traveled from time equal to a to time equal to x. So more specifically, y equal to this integral from a to x of f of t dt is the total distance traveled. From time equal to a seconds to time equal to x seconds. All right. So now, let's look at a moment somewhere in the middle. Let's look at like this little subsection right here. Let me use red. Actually, I don't even need to look at this. I'm sorry, I want to look at this more. Right, this is already what I already said. Right, this is in seconds, and this is. Sorry, I got kind of sidetracked there. So now here's what I want to say. Y is equal to the distance traveled. Y is our position at time t. So then I can take the derivative. dy dx. Right? The derivative with respect to x is equal to the rate of change of the distance at time equal to x. Again, I want to say it again. If I take the derivative of this with respect to x, I'm going to get the rate of change of the distance at that time equal to x. Which makes sense, right? We know that if we take the derivative position, we get velocity. So this is equal to the velocity at time equal to x. But we know a name for the function of the velocity. The velocity is f of t, right? The velocity of the runner at time t is equal to f of t. So the velocity of the runner at time t equal to x is equal to f of x. All right, so here's the big sum up. I have y equal to this integral. Great. I took the derivative of y equal to this integral, and I got the function. So here's what we said. we say that the derivative of the integral from a to x of f of t dt, which again, that's the thing that we called y. Why is that? Dy dx or d dx of y is equal to f of x. That's the fundamental theorem of calculus part 1. The derivative of an integral, upper limit x and lower limit constant, equals the function evaluated at x. It's kind of cool. Super cool. It's actually, I mean, it's pretty fundamental. Okay. So, what does this mean for us? Well, sometimes people like to ask some, let me erase this other side. I don't think it's going to work. It means that I can say, well, what if I have something like f of x? I don't want that. I don't want that notation. Let's say I have y equal to the integral from 2 to x of t squared dt. And I want to find the derivative of that. Well, I can either just say the derivative here, dy dx, is equal to x squared. But there's a reason this works. The reason it works is, well, we could anti-differentiate this. We actually, I mean, we could use the limit definition of the integral to find this. Do I want to do that? I kind of do. Let's do that. Let's find this using the limit definition of the integral. So, okay, it's going to be kind of gross. Do I really want to do that? Not so much, really. Yeah, that seems like I could make it a little bit nicer. So I'm going to show you the kind of I guess the shortcut way. So we could actually calculate this. The integral from 2 to x of t. You know what? Let me make it a little bit easier. Let's just do t instead. About that. So here's what we saw before. We saw before that the integral from 0 to any number b of x, right? That's equal to b squared over 2. So I wanted to find the integral from, say, 2 to x of t. I could just use geometry. I'm trying to find this area. I know it's the area of the big triangle minus the area of the small triangle. The area of the big triangle, oh, sorry, I should call this y equal to t, not y equal to x. Sorry about that. The area of the big triangle, well, let's see. The area of the big triangle is base times height times 1/2. That's going to be 1/2 x squared. The area of the small triangle, base is 2, height is also 2. So it's 1/2 times 2 squared. Right, literally I'm just using the fact that you could write this as the integral from 0 to x of t minus the integral from 0 to 2 of t. I'm literally taking the area under the curve from here to here and subtracting out this area there. So you get this. You get 1/2 x squared minus 2. All right, so let me ask everybody. What's the derivative of 1/2 x squared? It's x. The derivative of the integral of the function t from 2 to x is just the same function, but we replace the t with the x. And it works for literally anything. So in a similar way, I could ask you, what's the derivative of the integral from 4 to x of, I don't know, something terrible, t to the 4th plus 6t. We can do the work, and we will do the work in a second, but the answer is straightforward. The answer is x to the 4th plus 6x. Let's show the work. So we know that we could evaluate this. Maybe we don't know. I'm telling you that we could evaluate this using the evaluation theorem, which is that you can take the antiderivative and plug in your endpoints. So this would be equal to the derivative of, let's see, so the antiderivative of this is t to the 5th over 5 plus 6t squared over 2, evaluated from 4 to x. You always plug in the top limit first, subtract, plug in the bottom limit second. So that's going to be the derivative of x to the 5th over 5 plus 6 times x squared over 2 minus 4 to the 5th over 5 minus 6 times 4 squared over 2. Okay. So what's the derivative of x to the 5th over 5? And that's 5x to the 4th over 5. What's the derivative of 6x squared over 2? Oh, that's 6 times 2x over 2. What's the derivative of 4 to the 5th over 5? 0. What's the derivative of 6 times 4 squared over 2? Oh, also 0. Because they're constants and the derivative is 0. So look, we exactly end up with x to the 4th plus 6x, which is the same function we started out with, just with a different variable. So again, I'm going to say, when you take the derivative of the integral of some function of t, and your limits of integration are a constant to x, your answer, your derivative of that integral is just the function you started with, just using x instead of t's. Questions about this so far?
I do have a quick question, James.
Yeah.
So for like the when we were like minus and then parentheses 4 to the 5th divided by 5, would that be a plus or a minus?
Oh yeah, that should be a plus. I'm sorry. Yeah, it's a plus. Apologies. Yeah.
Okay. Yeah, I just wanted to clarify. Thank you, James.
I appreciate the clarification. So let me show you the second part. The second part that I've already kind of used a few times to justify some things. But so knowing the first part of the fundamental theorem of calculus tells us then the part that we really care about. We do talk about the first part because it's important, but check this out. So we know, because we just showed it, the derivative of the integral from a to x of f of t dt is equal to f of x. Again, I want to make sure everyone is super extra cool with this, because I'm going to say something really important next. All right. So here's what we know. We know that if the derivative of something is equal to a function, then, how do I say this? Let me say it this way. If the derivative of g of x is equal to f of x, then g of x is an antiderivative of f of x. Full stop. Pen's just trying to run out here. Get some new ink. Not a new tattoo, just a new pen ink. Okay, so what that means is this thing here, this is an antiderivative of little f of x by definition. Okay, great. So here's what we're going to say. That thing, a to x of f of t dt is equal to, I'm going to use the typical notation for an antiderivative, which is capital F of x plus the constant. And again, right, it should be noted that capital F of x is an antiderivative, meaning we know that capital F prime of x is equal to little f of x. Right, that's what it means for capital F to be an antiderivative of little f. Derivative of capital F is equal to little f. All right, here's the slick part. Maybe we didn't talk about this yet. I'm going to show you the slick part. So let me ask everybody. So I'm just going to replace x with something very convenient. I'm going to replace x with a. So the integral from a to a of f of t dt equals capital F of a plus c. Can anybody tell me, what do you get when you do the integral from a to a? A big old 0. Right, because we have no width. So that means 0 equals f of a plus c, which means c is equal to negative capital F of a. Great, we solve for the constant. So now here's what we've got. Yeah, I can leave this here. We've got that the integral from a to x of f of t dt equals capital F of x minus capital F of a. But then we're going to plug in the number we actually want. I'm going to use b there. The integral from a to b of f of t dt is equal to capital F of b minus capital F of a. But that's exactly the evaluation theorem for integrals. If you want to find the integral of a function, I should say the definite integral of a function from a to b, you find the antiderivative of that function, you plug in b, subtract, you plug in a. How great. And then we usually stop using t's here because we're like, oh, I can use some x's instead. So typically the way it's actually written is the following. The integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is an antiderivative of little f. Now, most people don't write it like this actually. What they do is they say it's the antiderivative capital F of x evaluated between a and b. And this notation means you plug in the top one first, subtract, then plug in the bottom one. So I know it feels like maybe that happened really fast, but we literally just proved the second part of the fundamental theorem calculus, which says that if you want to find the definite integral of a function from a to b, find the antiderivative, you plug in those points, boom, you're done. Yeah, kind of great. So let's see.
Wait, James, I just want to make sure for like the little box you just squared, it's supposed to be f of an x, right, instead of a t in this situation.
Sorry, say that one more time.
The little, for where you wrote inside of the little box that you just did.
Up here?
Yeah, like the integral from a to b, that's supposed to be an x, right, not a t.
No, it's supposed to be. Oh yeah, that's an x right there.
Okay.
So it's the integral from a to b of f of x dx equals capital F of B minus capital F of A.
Yeah.
Capital F of X divided by B. You could totally use T's there instead, right? It would be perfectly valid to use the variable T there and there and there. We just usually use X.
Okay, makes sense, James. Thank you.
But any variable you could use U, you could use S, you could use Y. It doesn't really actually matter as long as you're consistent. But typically X is the variable of choice for graphical reasons. So now, hopefully, maybe you believe me a little bit more when I say, oh yeah, the integral from 4 to x of t to the 4th plus 6t, I anti-differentiate t to the 4th plus 6t. I get t to the 5th over 5 plus 6t squared over 2. I plug in my limits of integration. I get x to the 5th over 5 plus 6x squared over 2 minus 4 to the 5th over 5 plus 6 times 4 squared over 2. And then if I differentiate that, the derivative of this part is totally just 0 because this part's a constant. And the derivative of this part gets you back to the function you started with. So let's look at a few more examples. Whoops. Sorry. Okay. So I should also point out, this is why we use the integral notation for an antiderivative. Because when you find the definite integral, you use the antiderivative to evaluate it, right? If I was going to find, say, the area under the curve from, I don't know, 0 to pi of, I don't know, x plus cosine, let's do sine of x, sure. The way I find the area under the curve is I find the antiderivative of that. So it's x squared over 2 plus negative cosine of x. I find it is minus cosine of x. Right? The antiderivative sign is negative cosine of x. Evaluated from 0 to pi. So we plug in pi first. We get pi squared over 2 minus cosine of pi. Minus, we plug in 0. 0 squared over 2 minus cosine of 0. Okay, so I get pi squared over 2. Cosine of pi is negative 1. Minus 0 squared over 2 is just 0. Minus cosine of 0 is 1. So I end up with pi squared over 2 plus 1 plus 1. So I get pi squared over 2 plus 2. That would be the area under this curve from 0 to pi. But if I just said, I want to know what the antiderivative of x plus sine of x is, well, I would use this notation. Right, and say, okay, I want to find the antiderivative. The antiderivative of x is x squared over 2. The antiderivative of sine of x is cosine of x. And then, since I'm talking about any antiderivative, I'm going to put on a plus c. So when you have limits of integration, this is a definite integral. And your answer should always be a number. On the other hand, this one here, this one doesn't have any limits of integration. This is an indefinite integral. Or in other words, AKA the antiderivative. I really should say an antiderivative, or the most general antiderivative. And here your answer is a function. So when you have limits of integration, you're finding a definite integral and you're getting some some number that represents area between curves or under a curve. When you have an indefinite integral where you don't have any limits of integration, you're finding the antiderivative, which is always going to be just a function. Very related to each other, right? Both of them, you're using the antiderivative. You're saying, oh, I can find the area under this curve using the second part of the fundamental theorem of calculus, taking the antiderivative of this function and then plugging in your limits of integration. Whereas here, I'm just saying, what's the antiderivative of this function? Oh, I'm just going to answer the function. But that's why this notation gets used for this, because it's so related to the antiderivative.